Okay, so let's talk about searching, right? Like when you have just tons of information. Imagine trying to find, I don't know, a single number or maybe a specific name buried deep in this mountain of data. If you had to just look at every single item one by one, well, you'd be there forever, basically.
Oh, absolutely. Like flipping through a massive old phone book, page by painful page, you're just hoping you stumble across it.
Yeah, exactly. There just has to be a better way.
And there is a much better way, provided, and this is the key thing, your information is organized in a very particular way.
Okay, so that organization is critical.
It is. And if that data is sorted,
Ah, sorted.
bingo. If your data is sorted, then you unlock the power of, well, one of the most fundamental and honestly breathtakingly efficient algorithms out there,
Yeah.
binary search.
Binary search. Right. It's a classic for a reason, I suppose.
It really is. The concept is just so elegant, so powerful. Once you really get it, you kind of start seeing its logic pop up in different places.
And that's exactly what we're diving into today. We're using the 10.1 binary search section from the Hello Algo resource as our guide. Our mission here is to really, unpack binary search completely, see how it works step by step, get a real feel for why it's so fast, but also, crucially, understand its limitations. Because it's not always the answer. The goal is for you listening to walk away with a solid understanding that actually sticks.
Yeah, absolutely. Because at its heart, binary search is, well, it's the ultimate divide and conquer strategy when you're dealing with sorted data. You basically keep cutting the area you need to search in half again and again. You instantly throw out huge chunks of data where you know your target just can't be.
Okay, let's nail down the basic problem then, like how Hello Algo sets it up. You've got this array of numbers, let's call it nums, and the really important bit, it's sorted,
Hmm.
ascending order. And for this basic example, let's say no duplicate numbers.
Right, keeping it simple to start.
And you have a specific number you're looking for, the target, your job. Find the index where that target is hiding in the array. If it's not in there at all, you just return -1.
Right.
Simple enough goal.
Exactly. And let's say, the most common way to tackle this, the one often recommended, uses what's called a closed interval. Think of this interval as the current slice of the array where your target might still be hiding.
Right. And initially, that slices the whole array, right?
Precisely. So you set up boundaries. You need 2 pointers, maybe call them I for the start and J for the end. You start I at index 0, the very first element, and J points to the very last element, which is at index n1 if there are n elements total.
Okay, I at 0, J at n1. And this interval, written like I, J with square brackets, is closed because...
Because it includes both ends. The element at index I and the element at index J are both still considered possibilities. They're inside the search zone.
Got it. So how long do we keep searching within this zone?
Well, you keep going as long as there's a valid zone to check, which means as long as your starting pointer hasn't gone past your ending pointer J. So the condition for your loop is while IJ.
While IJ. Makes sense.
Oh,
if
yeah.
I ever becomes greater than J.
Then your search space has shrunk to nothing. The interval is empty. The target wasn't there.
Okay, so inside that while loop, what's the main action?
The core idea. Find the middle. You calculate the index of the middle element within your current IJ interval. Let's call this middle index M. Now, the obvious way to calculate it might seem like M floor I plus J2.
Yeah, average the start and end indices, take the floor. Seems straightforward.
And it works.
Yeah.
Most of the time. But here's a little detail, a potential snag that the source material rightly points out. If you're dealing with a massive array, like truly huge, then I and J themselves could be very large numbers. And adding them together first, I plus J, could, in some programming languages or systems, actually exceed the maximum value an integer can hold. It's called integer overflow.
Oh, wow. Okay, that's a nasty bug just waiting to happen if you're working with big data. So there's a safer way.
There is. A more robust formula is M equals floor I plus JI2.
M floor I plus JI2. Let me think that through. JI is the width of the current interval.
Exactly. You find the width, divide it by 2 to get halfway across, and then add that half width to the starting point I. This way, you avoid adding 2 potentially massive numbers, I and J, directly. It achieves the same result but avoids the overflow risk. It's a good habit to get into.
Okay, that's a really valuable implementation tip. So M e floor I plus JI2. We've safely found our middle index M. Now what?
Now comes the decision. You look at the actual value stored at that middle index, which is numism,
Yeah.
and you compare that value to your target.
This is the conquer plea of divide and conquer.
You got it. This comparison is what lets you throw away half the remaining search space. There are really only 3 possibilities. Possibility 1, the value in the middle, numism, is less than your target.
Okay, if the middle value is too small and the array is sorted low to high,
Then where must the target be if it's in the array at all?
it has to be somewhere to the right of M, because everything at M or to its left is even smaller.
Precisely. So you can completely discard the entire left half of your current interval, including the middle element M itself, because you know it's too small. Your new search interval needs to start 1 position after M, so it becomes M plus 1J.
And you update the starting pointer, I to M plus 1, I equal M plus 1.
Perfect. You've just cut your search space roughly in half.
Okay, possibility 2.
Possibility 2. Numism is greater than the target, so the middle value is too big.
Right, same logic, just reverse. If the middle is too big, the target, if it exists.
Must be in the left half. Everything at M or to its right is too large.
Exactly. So you discard M and everything to its right. Your new interval becomes I M1.
And this time you update the ending pointer J, so J equals M1.
You're nailing it. And the third possibility is the happy path.
Numism is equal to the target.
Bingo. You found it. The element is right there at index M. Game over, you return M. That's the goal. So the loop just keeps going, find the middle, compare, shrink the interval by updating either I or J.
Until one of 2 things happens. Either you hit that third case and return M because you found the target.
Or the interval shrinks so much that it actually becomes greater than J.
Right. At that point, the while J condition becomes false, the loop terminates. And since you didn't find the target inside the loop,
You know it's not in the array. And that's when you return exef1.
exactly. That's the whole process for the closed interval IJ approach. It's clean, it's logical.
It really is. That step-by-step narrowing down makes perfect sense. Now, you mentioned this is the common way, but our source also talks about another approach, something about how the interval is defined.
Yes, that's right. You'll definitely encounter implementations that use what's called a left-closed, right-open interval. The notation usually looks like I, J, with a square bracket on the left and a parenthesis on the right.
IJ. Okay, so left boundary I is included, but right boundary J is not included.
Exactly. J marks the first element that is outside the potential search space.
Huh. Okay, how does that change the setup?
The initialization is slightly different. I still starts at 0, but J is initialized to lennums, which is n. So J actually starts 1 position past the last element of the array. The initial interval is 0n.
0n. Okay, covering indices 0 up to, but not including n. And the loop condition. Does it still run while I equal j?
No, that changes too. The loop runs while ij. Think about it. The interval ij is considered empty the moment I equals j. If I and j are the same, there are no indices x such that I equals xj.
Right. While ij. Got it.
Yeah.
Midpoint calculation, still the safe m equals I plus ji2 using integer division.
Yep, that stays the same. The tricky part, or at least the part where you have to be careful, is adjusting the interval after the comparison.
Okay, let's walk through those cases again for ij.
Sure. Case 1, numism target. Same logic, target must be to the right. So the new interval should start after m. It becomes m plus 1j. You update I equals m plus 1. That's identical to the closed interval method.
Okay, I equals m plus 1. Easy enough.
Case 2, numism target. Middle is too big. Target must be to the left of m. The new interval should be im.
I am, so we update j.
Yes, you update jm. Notice it's jm, not jm1.
Why jm?
Because m itself is too large, so we want it excluded from the next search space. And in the ij notation, the right boundary j is already exclusive, so setting jm correctly makes m the new exclusive upper bound.
Oh, okay, that's the subtle difference.
Yeah.
Because j represents the first element not included, so setting jm excludes m.
Got it. It's a
Yeah.
common point of confusion.
Yeah.
And case 3, numism equals target. Same as before you found it, return m.
And if the loop finishes, that happens when ij.
Correct. If the loop finishes because I equals j and you haven't returned m, the target isn't there, return neglen 1.
It's the same result in the end, but the loop condition, ij vs I, and that j update, jm vs j, are the key differences to watch out for.
Precisely. And the source actually suggests, and I tend to agree, that the first method, the closed interval ij, might be a bit more intuitive for many people. The update rules, I equals m plus 1 and j equals m1, are kind of symmetrical. It feels a little cleaner, perhaps less prone to off-by-one errors than the I equal m plus 1, j equals m updates in the right open approach.
Yeah, I can see that. The symmetry does feel a bit more straightforward, less likely to mix up. Okay, so we've dissected the mechanics, the two main ways to implement it. Let's get to the payoff. Why is binary search such a big deal? What are the advantages?
Okay, the number one reason, the headline act, is its incredible speed, especially on large amounts of data. We talk about its time complexity being O log n.
O log n, big O notation, we hear it a lot. Let's really break down what that means in practice, like for finding your target number.
It means the number of steps, the number of comparisons you need to make, grows logarithmically with the size of your input array, n. What does that mean? Because you're having the search space every single step, the number of steps grows incredibly slowly as n gets bigger and bigger.
Okay, slow growth is good, but how slow is slow? The Hello Algo source had a really powerful example for this, right?
It did. It really drives the point home. Imagine an array with n with 220. That's 1,048,576 over a million elements.
Over a million, okay.
Now, if you were stuck using a simple linear search, just starting at the beginning and checking every single element one by one.
In the worst case, if the element is at the very end or not there at all, you'd have to look at all million-plus items.
Exactly. Potentially 1,048,576 steps. Could take a while.
Yeah, just a bit. Okay, so what about binary search on that same million-element sorted array?
Because you have the search space each time, the number of steps is roughly the base 2 logarithm of n. So log base 2 of 220.
The log base 2 of 2 to the power of 20 is just 20.
20. 20 steps?
Wait, seriously. 20 steps to find one item out of over a million, compared to potentially over a million steps with linear search.
That's it. 20 versus a million. That is the staggering difference. That's why binary search is absolutely fundamental when you're dealing with large sorted data sets. It's not just incrementally faster. It's like a different dimension of efficiency.
20 steps.
Yeah.
I'm still trying to wrap my head around that scaling. It's phenomenal. Okay, so speed is obviously the killer feature. What about memory usage? Does it need a lot of extra space?
That's the other beautiful part. No, it's incredibly memory efficient. Its space complexity is O1.
O1, meaning constant space.
Right. It only needs a fixed small amount extra memory to store those few pointers, I, J, M, and maybe a temporary variable or two. That amount of memory doesn't change whether your array has 10 elements or 10 billion elements.
So it's not like creating copies of parts of the array or building big helper structures on the side.
Not at all. Compare that to something like, say, building a hash table for fast lookups. Hash tables can be very fast, but they often require significant extra memory to store the table itself. Binary search is lean.
Okay, so mind-blowing speed, O-log time, and super efficient on memory space. It's sounding like the perfect algorithm. But there's always a but, isn't there? No algorithm is perfect for everything. When should we not reach for binary search?
Absolutely. Knowing the limitations is just as important as knowing the benefits. And the biggest limitation, the absolute non-negotiable requirement we started with.
The data has to be sorted.
That's the one. If your data isn't already sorted, binary search is useless on its own.
And sorting takes time, right? Especially for big data sets.
It absolutely does. Efficient sorting algorithms like the common ones, merge sort or quick sort, generally run in O n log n time. So think about this scenario. Your data is unsorted, and you only need to find one single item in it just once.
Okay.
To use binary search, you'd first have to sort the data, which costs O n log n. Then you'd do the binary search, which is super fast, O log n. But the total time is dominated by that sorting step. It's O n log n overall.
Right. But what if I just did a linear search on the original unsorted data?
Linear search on unsorted data is just O n. You just scan through it once.
So O n for linear search is actually faster than O n log n for sort than binary search if you only need to search once.
Exactly. That's a critical point. Binary search really pays off when the data is already sorted or when you're going to be doing many searches on the same data so the initial cost of sorting gets spread out or amortized over all those fast searches.
Okay, that makes sense. Sorting cost matters. What else limits it?
Well, related to sorting, what if your data changes a lot? If you're constantly inserting new items or deleting old ones.
You'd have to keep it sorted, right? Which sounds like it could be a pain with an array.
It can be a huge pain. If you insert an element into the middle of a sorted array or delete one, you often have to shift all the subsequent elements over to maintain the order and fill the gap.
And shifting elements in an array, that can take time proportional to the number of elements you shift, right? Potentially, O(n), time for a single insertion or deletion in the worst case.
Precisely. So if your data set is very dynamic, with lots of insertions and deletions, the cost of constantly resorting or maintaining that sorted array structure might completely outweigh the benefit you get from the fast O-long searches.
So for highly dynamic data, maybe other structures are better, even if searching isn't quite as fast as a login.
Exactly. Things like balanced binary search trees or maybe even hash tables might offer a better overall trade-off between search speed and modification speed in those cases.
Okay. Another limitation mentioned in the source had to do with the data structure itself, not just whether it's sorted.
Yes. Binary search relies fundamentally on one crucial property of arrays: random access, the ability to jump directly to any element using its index, nums it is, in constant time, O1.
Arrays let you do that, but what if your sorted data was stored differently, like in a linked list?
Ah, good question. In a standard linked list, you don't have random access. To get to the middle element, you'd have to start at the beginning and traverse through the nodes one by one.
So just finding the element at the calculated midpoint index m might require walking through m nodes, which could take,
Up to ON time, in the worst case, just to find the midpoint value.
ouch, so that completely defeats the purpose.
Yeah.
The O log n magic relies on being able to jump to the middle in O1 time.
Exactly. So binary search in its standard form is just not efficient for data structures like linked lists that lack fast random access. You need that array-like structure.
Right. And there was one more limitation mentioned, which sounds almost weird after hearing about the 20 versus a million example.
You mean the point about very small data sets?
Yeah. The source says that for really small arrays, linear search might actually be faster sometimes.
Oh.
How can that be?
It does seem counterintuitive, doesn't it? But think about the actual operations involved in each step. Linear search is dead simple. Look at the element, compare it to the target, maybe 1-2 operations per element, very little overhead. Binary search in each step has to calculate the midpoint, I plus ji2, which involves subtraction, division, addition. Then it accesses numism. Then it compares numism to the target. Then it updates either I or ji. The source suggests this might be, say, 4 to 6 basic operations per step for binary search.
So more work per step, even though there are fewer steps overall for large-hand.
Exactly. For a tiny array, maybe just 5 or 10 elements, the total number of operations involved in doing, say, 3 or 4 steps of binary search with its 4 to 6 operations per step might actually be more than just doing 5 or 10 simple comparisons in a linear search.
It's the constant factor overhead. The O log n scaling only really dominates and provides that massive advantage when n is large enough for the logarithmic reduction in the number of steps to vastly outweigh the slightly higher number of operations within each step.
You've got it. So for truly tiny data sets, the simplicity of linear search can sometimes win out. It's all about context and scale.
Okay, let's try and wrap this up then. Binary search. It's incredibly powerful, incredibly fast for finding things. We're talking O log n time, which is just phenomenal on large data sets.
And it's light on memory, too, O1, space complexity. It's a beautiful demonstration of how organizing your data first by sorting it can enable huge efficiencies later.
But, and these are important buts, it comes with strict requirements. Your data must be sorted beforehand.
Non-negotiable.
And it needs to be in a data structure that allows that instant O1 jump to any element, like an array. Not great for linked lists.
Right. And remember the trade-offs. If you only search once on unsorted data, sorting first is likely slower than just doing a linear scan.
And if the data changes constantly, the cost of keeping it sorted might kill the benefits.
And finally, yes, for very, very small arrays, the overhead might mean linear is just fine, or even slightly faster.
Understanding this algorithm, though, it's about more than just code. That core idea, divide and conquer, repeatedly having the problem, that's a really powerful mental model, isn't it?
It absolutely is. It teaches you about optimization, about thinking strategically about how information is structured and accessed.
So, for everyone listening, now that you've got this idea of binary search thinking, maybe reflect on where else you use it, perhaps without even realizing it. Like if you're looking for a word in a dictionary or trying to guess a number someone's thinking of between 1 and 100, are you already applying this kind of halving strategy?
Yeah, or think bigger. What other problems in your work or just in the world involve searching through vast amounts of information? If that information could somehow be perfectly ordered, could this divide and conquer approach unlock efficiencies we haven't even imagined yet? It's a pattern with implications far beyond just searching arrays.